Hi, welcome to Algebra 2 Common Core. In this lesson we're going to continue working with polynomial equations and see how the equations, the graphs, and the zeros of polynomials all work together. We can use our knowledge about graphs of polynomials and their zeros or roots to find the equations of polynomial functions. So looking at example number 1, we see that we have a quadratic function. Remember that a quadratic function has to have the equation with a standard form of y is equal to a times x squared plus b times x plus c. But we're actually going to be using our equation in intercept form or factored form. Let's identify the roots from the graph. So I see on the left side that the first root is occurring at -3, 0, and on the right side the other root is occurring at 4, 0. So given the two roots, x is equal to -3 and x is equal to +4, I know that I can write an equation of a parabola with those two roots. Y is equal to get a root of -3, I know that the factor x plus 3 has to be in the equation. To get a root of 4, I know that the factor x minus 4 must be in the equation. So you'll notice that this quadratic is in factored form, not in the standard form that I wrote above. Let's go ahead and check our equation to verify that the given point, in this case the point 2, -50, is on our parabola. So when I substitute 2 into my equation, I'm going to have 2 plus 3 times 2 minus 4, and I get the y-coordinate equal to 5 times -2, which is only -10. Now this seems to be a discrepancy because we thought that we were going to have a y-coordinate of -50. What seems to be going on with this parabola? So let's take a step back and look at example number 2, where we talk about the roots of quadratic equations, and then we'll come back and examine exercise number 1 again. So in example 2, we have 3 different equations that we want to find the factored form of. So it says, which of the following is the equation of a quadratic whose roots are -2 and 5? So y1 can be factored as, let's see here, x squared minus 3x minus 10. I'm going to factor that as x minus 5 times x plus 2. Now if I set those factors equal to 0 using my zero product property, I do get that the roots are x equals 5 and x equals -2. Going over to my graph, I see that I have a root at -2. I have a root at 5. And if I graph this one, and again, you might want to look at your graphing calculator on this, I'm going to get the following parabola for y1. So yes, this one does have roots of -2 and 5. Let's try y2. What we may notice in y2 is that we've got a GCF. So I'm going to take out that GCF of 2, and I'll be left with the factors x squared minus 3x minus 10. I think we just saw that a minute ago, so we know that this can be factored as 2 times x minus 5 times x plus 2. And again, if I set this equal to 0, I get the two roots, x equals 5 and x equals -2. But for this one, I saw that it had a coefficient of 2. We know that's going to vertically stretch my graph. So let's go ahead and graph this one. I'm going to graph this one in red. It still crosses the x-axis at -2 and +5, but all of the y-coordinates are doubled, so my graph is going to look something like this for y2. Let's go one step further and try y3. And in the case of y3, we see that we also have a GCF, but this time the GCF is 4. Factor out that 4, so I'm left with x squared minus 3x minus 10. Again, it looks familiar. So I'm seeing that y3 is going to be 4 times x minus 5 times x plus 2 with the same roots that I saw before. But this time my stretch is going to be a stretch of 4. So let's go ahead and graph that one stretched even further. So this parabola is going to look something like this. And the black one is going to be y3. So what we notice as a conclusion here is that all three equations do have roots at x equals -2 and x equals 5. But what's different about them is that they each had a different leading coefficient. That leading coefficient did not change the roots. All that happened with that leading coefficient, the a value, changed our graph because it was a vertical, and in the case of all the ones that we saw here, they were vertical stretches. Now we, of course, could have also had a vertical compression if the a value is less than 1. So we're going to go back and look at example number 1 and see how we can apply this knowledge to see if we can find the equation for the parabola that we were given. So far we had that the equation was going to have the factors x plus 3 and x minus 4. But what we didn't take into account is that our graph may have been stretched. So let's see if there was a stretch incorporated here. Let's see if there was an a that had to be multiplied by the factors. What we want to do is use the coordinates of the point that has to be on our parabola and substitute those coordinates in. So I'm going to say my y coordinate has to be -50. I want to solve for the a value when x is equal to 2. So I'm going to substitute 2 in for each x, so 2 plus 3 times 2 minus 4. That tells me that -50 would be equal to a times 5 times -2. So -10a has to equal -50. Dividing both sides by -10, I get that a is equal to 5. So that tells me that my original equation must have been y is equal to 5 times x plus 3 times x minus 4. That answer makes sense because when we first of all used our factored form that didn't have the a, we got the conclusion that 2 -10 was on our parabola. But actually we wanted the point 2 -50, so that tells me that I must have had to multiply by 5. So multiplying by 5 is that vertical stretch. Now, of course, we all know that we can then multiply this out to get the standard form of the equation of the parabola. So 5 times x squared minus x minus 12. So the standard form is going to be 5x squared minus 5x minus 60. Let's go ahead with example number 3, where we want to create the equation of a cubic function this time. Eventually we're going to get this cubic function in standard form, but we're going to start with it in intercept form to begin with. Our x-intercepts are going to be -4, 2, and 5. So let's jot those down, -4, 2, and 5. Now, along with knowing the intercepts, we also have to know an additional point on the polynomial so that we'll be able to make sure that we can solve for any vertical stretches involved. I'm first of all going to go ahead and plot these points. So I know that -4 is one of our roots, +2, and +5. So if x equals -4 is a root, that means that x plus 4 had to be a factor in this polynomial equation. So I'm going to set it up as y equals a times x plus 4. If 2 is a root, that tells me that x minus 2 has to be a factor. And if 5 is a root, that tells me that x minus 5 has to be a factor. Now before I proceed in multiplying this out to put it in standard form, it's always a lot easier to plug the point into the factored form to solve for my a value. So the y coordinate is 20. I want to solve for a. Substituting 6 in for x, I've got 6 plus 4 times 6 minus 2 times 6 minus 5. So 20 is equal to a times 10 times 4 times 1. So 40a is equal to 20, and a must be equal to 1/2. Now, to put this in standard form, let's go ahead and substitute that value of a into this equation right here. So I'm going to have y is equal to 1/2 times x plus 4 times x minus 2 times x minus 5. Now because I have 3 factors to multiply together, I'm going to multiply 2 of them at once. So let's say x plus 4 times x minus 2. Double distribute, so that's giving me x squared plus 2x minus 8 multiplied by x minus 5. That's nice and easy to multiply using my box multiplication. I have a trinomial x squared, 2x, and negative 8, and I want to multiply by x minus 5. And when I do that, I'm getting x cubed, 2x squared, minus 8x, negative 5x squared, negative 10x, and positive 40. So let's write down the result of that multiplication. 1/2 times x cubed. Add together your x squared terms, so that's going to be a minus 3x squared. Add your x terms together, so that's going to be a minus 18x. And then plus 40. Distribute the 1/2, and I'm getting 1/2 x cubed minus 3/2 x squared minus 9x plus 20. I'm going to leave it to you to plug that into your graphing calculator to see what the graph is going to look like. If we know that our information has us crossing the x-axis at -4, 2, and 5, the other thing that I can take a look at is this constant term. If x is equal to 0, then that's telling me that the y-intercept has to be equal to 20. So on my graph, I know that I'm going to come up here and hit the y-axis at 20. I ended up with an a value that was positive, so that tells me that for a cubic, my graph should rise through that intercept, come back down, and back up again, and my graph will look something like that. In example number 4, we are again going to create the equation of a cubic function in standard form, but this time you'll notice that I have one more piece of information. There's a double zero at -2. We had some information about double zeros or a multiplicity of 2 in our last lesson, so let's see what that's going to do to affect our cubic function. We also have another 0 at x equals 4. So let's see here, we're going to say that our roots, those are occurring at x is equal to 4, and we know that we have a double 0 at -2. My factored form of this is going to be y is equal to, let's account for that possible multiplier a that could be a vertical stretch or a compression. My first root is occurring at x equals 4, so that's going to give me a factor of x minus 4. Now because I have a double zero at x equals -2, the factor x plus 2 is actually going to occur twice in my polynomial. Now let's go back and use the information about our y-intercept at 16. A y-intercept is really just telling us the coordinates of a point. When x is 0, y is 16. So let's plug that information in for y and for x, do a substitution. So 16 is equal to a times, now we're using 0 for x, so that's going to be -4 times 2 squared. So in this case, I'm getting that 16 is equal to -16a, so a must be equal to -1. Now, of course, a negative leading coefficient is going to affect our graph as well. Let's go back and put that a value into our equation. We'll answer this next question in just a minute. So y is equal to -1. I'm going to go ahead and multiply the x plus 2's together. So that's giving me x squared plus 4x plus 4. Now do your box multiplication again. I'm multiplying a binomial x minus 4 times a trinomial x squared plus 4x plus 4. So I'm getting x cubed plus 4x squared plus 4x, -4x squared, oh that's going to be good because they cancel, -16x and -16. So putting this into our equation, we have y is equal to -1 times, my product would be x cubed minus 12x minus 16. Distributing the negative, that gives me y is equal to -x cubed plus 12x plus 16. That's good news because I see that that constant value of 16 is giving me an x-intercept. Oh, I'm sorry, not an x-intercept. That's giving me a y-intercept. When x is 0, it's a y-intercept equal to 16. Going back to answer our question, what happens at the double zero on the graph? Remember from our last lesson, when we have a double zero, the graph doesn't cross the x-axis at that point. It basically bounces off of the x-axis. So let's plot these points and see what our graph looks like. I have a double zero at -2, so that's right there. I have a 0 at +4, so that's right there. Now because my leading coefficient this time is negative, that's going to affect how my graph begins. So my graph is going to begin coming down from the top left, bounce off of the x-axis right here, cross the y-axis at 16, and come back down and go through the x-axis at 4. So you see that while it has two real roots, one of the roots turned out to be a point where the graph didn't cross the x-axis, it bounced off of the x-axis. And that's because it's one of those double zeros. Let's take a look at our last example and see the real power of being able to find equations of polynomials just by knowing the roots and one additional point on the polynomial. So you notice that for this graph, I'm given the graph so I can identify what the roots are. Clearly I see that I have a root at -30, and that's a crossing root, so that tells me that it's just got a multiplicity of 1. But then I have another root at -1, But that's one of those roots where the graph bounces off the x-axis. So that one's going to be a double zero at -1. And then there's another root at x equals 2, so this is going to be a 2, 0, and again, that's going to be a multiplicity of 1. So we're going to make our standard equation by starting with the factored form. Y is equal to a times, the root -3 would come from the factor x plus 3. The root 2 would come from the factor x minus 2. And then the double root at -1 would come from the factor x plus 1, and it would need to have a power or a multiplicity of 2. Now, in addition to the roots, I was also given an ordered pair for a point on my polynomial. So let's go ahead and plug that point in and substitute 8 for y in order to solve for the a value. -2 is being substituted for x, so -2 plus 3, -2 minus 2, and -2 plus 1. That one's being squared. So for this one, I get 8 is equal to a times 1 times -4 times +1. So I'm ending up with a times -4. That tells me that a must be equal to -2. Go back and substitute that value of a in. So I have -2. I'm going to multiply these next two together, so I get x squared plus x minus 6. Let's square x plus 1, so that's going to be x squared plus 2x plus 1. Now, because I'm trying to multiply a trinomial times a trinomial, I'm going to need a 3 by 3 box this time. So I've got x squared, x, and minus 6. I've got x squared, 2x, and 1. Do all of your multiplies, so x to the 4th, x to the 3rd, minus 6x squared, 2x cubed, 2x squared, minus 12x, x squared, x, and -6. So putting together all my like terms, I now have -2 times x to the 4th plus 3x cubed minus 3x squared minus 11x minus 6. And lastly, let's distribute the -2. So my final equation for my polynomial, -2x to the 4th minus 6x to the 3rd plus 6x squared plus 22x plus 12. Now, of course, the easiest way to check this, we're going to do a check with this on our calculator. So plug this equation into y1 and be sure that we match the graph on your calculator to the graph that I was originally given. So notice how powerful this method is to be able to find an equation of any polynomial if given the roots and at least 1 point on the polynomial, as well as our knowledge of factors, roots, and whether we have an even or an odd exponent as our leading term, and whether the coefficient turns out to be a positive or a negative leading coefficient. All of this has come together to give us a lot of information about these polynomials. We'll be working on some of these polynomial graphs in class tomorrow. Have a great night, and we'll see you next time.